Welcome to Deep Dive with Phil and Emily. Have you heard our theme song? You really should. It's a total banger. Anyway, today we're taking a deep dive into the world of support vector machines. You know, SVMs? You sent us some material on them?
Yeah, some lecture notes and slides.
Yeah.
Looks like some fascinating stuff from Professor Wu. We're gonna break it all down for you.
Yeah.
Extract the key insights without, getting bogged down in all the lecture hall details.
Exactly. So imagine you have like a bunch of data points and you want to like separate them into two distinct groups. Think of it like sorting a bowl of M&Ms by color.
Right. So SVMs are all about finding the best line to make that separation. But here's the catch, right? There could be tons of lines that could technically do the job.
Right. Like you could draw a line that just barely separates the M&Ms.
Right.
Or you could draw one that gives them plenty of space.
Yeah, and that's where SVMs get really interesting. They don't just settle for any dividing line. They're looking for the line with the largest margin, right? Think of it as creating the biggest possible buffer zone between the two groups of M&Ms.
Okay, I'm starting to see how this works. But like, how do SVMs actually find this magical line with the maximum margin?
Well, it involves a bit of linear algebra. Professor Wu, he gets into some of the nitty-gritty in his lectures, talking about things like unit vectors and linear projections.
Unit vectors, linear projections. Sounds a bit intimidating.
It's not as scary as it sounds. Think of a unit vector like an arrow
Okay.
pointing in a specific direction, but with a length of exactly 1.
Okay, so it's like a standardized arrow that tells us which way to go.
Exactly. And linear projection is like shining a flashlight on that arrow
Okay.
and seeing where its shadow falls on another line. It's a way of figuring out the relationship between two vectors.
So how do these arrows and shadows help SVMs find the best separating line?
Well, these concepts are the building blocks for how SVMs measure distances and positions in the data space, right? They need to figure out how far each data point is from potential dividing lines and which points are closest to the boundary.
So they're using these tools to identify the support vectors.
Yes.
Those crucial data points that define the margin.
Precisely. Remember those M&Ms we talked about? The support vectors are like the M&Ms that are right on the edge of their respective groups, almost touching the dividing line.
Okay, so we've got our support vectors, and we know we want the biggest margin possible. But how does this translate into like a mathematical problem that the SVM can actually solve?
Right. That's where the concept of the objective function comes in. It's like a mathematical scorecard that tells us how good a particular separating line is.
So the higher the score, the better the line.
Exactly. And the objective function for SVMs takes into account both the correctness of the classification, meaning how well the line separates the data, and the size of the margin.
So it's not just about drawing any line that separates the data. It's about finding the line that does it with the most breathing room.
Right. And to simplify the math, we can set the magnitude of the line to 1.
Okay.
Multiplying a line by a constant doesn't change its direction, just its length, so we can scale it down without losing any information.
That makes sense. So we've got our objective function, and we've simplified the line equation a bit. What's next?
Well, we need to figure out the exact position of this line, right? In a regular line equation, you have the slope and the intercept. In the SVM world, the slope is represented by the weight vector, which we've been talking about with those unit vectors.
Okay, so the weight vector tells us the direction of the line, but what about the intercept?
That's represented by a value called b. And to find b, we need to project all those data points onto the weight vector. Remember our flashlight analogy?
I'm starting to see how this all comes together. We're projecting the data points onto the weight vector to figure out their positions relative to the line.
Exactly. And the midpoint between the support vectors, those M&Ms on the front lines, will give us the value of b.
So we're basically using the support vectors as landmarks to pinpoint the exact location of the separating line.
Precisely. And now that we have all the pieces of the puzzle, the weight vector, the value of b, and our simplified objective function, we can use a technique like gradient descent to find the optimal solution.
Gradient descent. That's our trusty algorithm for finding the best values for the weights in B that will maximize both the accuracy of the classification and the size of the margin.
You got it. And once we have those optimal values, we've got our SVM model ready to go.
This is amazing. We've gone from sorting M&Ms to understanding how SVMs use linear algebra and optimization to find the perfect dividing line. But I have a feeling there's even more to this story, right?
You're absolutely right. We've only scratched the surface. There are variations of this basic SVM model, like the soft margin SVM, which adds another layer of sophistication.
Okay, I'm definitely intrigued. Let's dive into that in the next part of our deep dive.
Sounds good to me. So remember how we talked about finding that perfect separating line with the maximum margin?
Yeah, like finding the ideal boundary between those M&Ms.
Well, in the real world, things aren't always so neat and tidy. Sometimes you might have a few rogue M&Ms that end up on the wrong side of the line.
Oh, I can see that happening. Like maybe you've got a couple of yellow M&Ms that snuck into the red pile.
Exactly. And that's where the soft margin SVM comes in. It's a more flexible approach that allows for some misclassifications.
So instead of rigidly forcing the line to perfectly separate every single data point, it gives a little bit of wiggle room.
Precisely. It's like saying, okay, we know there might be a few outliers, so let's not get too hung up on those. As long as the overall margin is still pretty good, we're happy.
But how does the SVM decide how much wiggle room to allow? Can't just let everything go haywire, right?
Of course not. There's a delicate balance to strike. If you're too lenient, you might end up with a line that doesn't really separate the data effectively. But if you're too strict, you might overfit the model to those few outliers.
Overfitting, what does that mean?
Imagine you're trying to draw a curve that passes through a bunch of dots on a graph.
Okay.
If you try to make the curve hit every single dot perfectly, you might end up with a really squiggly, complicated curve that doesn't generalize well to new data.
So it's like memorizing the answers to a test instead of actually understanding the concepts.
Exactly. And in the case of SVMs, overfitting would mean creating a separating line that's so focused on those few outliers that it doesn't do a good job of separating the majority of the data.
Okay, so we need to find a happy medium between being too strict and too lenient. But how does the soft margin SVM actually achieve that?
Well, remember that objective function we talked about, the one that scores how good a separating line is.
Yeah, the one that takes into account both the accuracy of the classification and the size of the margin.
Right. In the soft margin SVM, we introduce a penalty term that only kicks in when there's a misclassification.
So it's like a little slap on the wrist for
Yeah,
the SVM when it gets something wrong.
exactly. And the severity of that slap on the wrist is controlled by a parameter that we can adjust.
So we can fine-tune how forgiving the SVM is depending on how much we care about those outliers.
Precisely. And by introducing this penalty term, we're essentially telling the SVM, it's okay to make a few mistakes, but don't go overboard. Try to find a line that balances accuracy with a good margin, even if it means letting a few data points slip through the cracks.
That's really clever. So the soft margin SVM is all about finding a compromise between those two goals.
Absolutely. It's a more nuanced and realistic approach that recognizes that data in the real world is rarely perfect.
I'm starting to see how this soft margin approach would be much more practical for real-world applications.
Absolutely. But it gets even more interesting. Remember how we talked about those labels? The things that tell us which group each data point belongs to? Well, even those labels can be wrong sometimes.
Wait, you mean like mislabeling a red M&M as a yellow one?
Exactly. And just like those rogue M&Ms that ended up on the wrong side of the line, these mislabeled data points can also throw off the SVM.
So even if the SVM is doing its best to find the best separating line, it might be working with flawed information.
Precisely. It's like trying to solve a puzzle with some of the pieces in the wrong places.
So how do we handle these potential mislabelings? Do we just have to hope for the best?
Well, luckily there's a way to account for this in the SVM algorithm as well.
Really? I'm all ears. How does it work?
We add another term to our objective function. This term gives a bit of extra wiggle room to accommodate those potential errors in the labels themselves.
So it's not just about tolerating misclassifications by the SVM, but also tolerating potential errors in the data itself.
Precisely. We're essentially telling the SVM, look, we know the data might not be perfect, so don't freak out if things don't line up perfectly. Just try to find the best line you can, given the information you have.
That's pretty amazing.
Yeah.
So the soft margin SVM is not only flexible in terms of allowing for misclassifications, but it also takes into account the possibility of errors in the labels themselves.
Exactly. And by combining these ideas, we get a more robust and adaptable SVM model that can handle the complexities of real-world data. It's always a joy to explore these concepts and see how they connect to real-world applications.
Well, on that note, I think we've reached the end of our deep dive into the world of support vector machines. Hopefully you've learned something new and exciting today. And if you haven't already, go check out our theme song.
Absolutely.
Until next time.